Every day, people take risks, from betting on the roll of a die, a hand of cards, to forecasting the prices of futures on the commodity exchange. In the marketing world, being able to calculate your risks and make decisions based on these calculations is vital. In this program about decision-making and Bayesian analysis, we will introduce the basic mathematics of Bayesian analysis and give an example of how it may be applied in marketing. Bayesian analysis is a tool that helps you to make decisions that traditional approaches to probability cannot help you with. For example, in the marketing world, it is an integral part of the marketing effort to get some kind of research going, to get additional information. An important problem that many marketers face is, how much is the research effort worth? Traditional approaches to probability cannot help with this problem. Bayesian analysis can, and in this program, we will show you how. Every marketing student may not necessarily use Bayesian analysis on a daily basis, but in certain jobs or certain circumstances, it is invaluable, and you'll be expected to know how it works. And so this program will introduce you to Bayesian analysis and an application in the area of marketing. We are right now at Loyola University in the Department of Mathematical Sciences, and I am going to interview Professor Gerald Funk, who's a professor here in statistics. Bayesian statistics have been referenced in the business field, such as marketing, finance, management science, and operations research. As a professor in statistics, can you please comment on this trend? Specifically, why are these business disciplines using Bayesian statistics now?
Okay, the advantage of using Bayesian statistics is it gives you a common reference point in problems where you're trying to analyze risks of different opportunities. And I think that perhaps the trend is to be using it more, goes hand in hand with the availability of handling the mathematical computations with the ease of putting things on computers to do analysis. So there's a larger pool of people with the technical training to use these methods.
In terms of looking toward the future, we notice more and more sophisticated models are being used by businesses in decision-making and forecasting. Do you think Bayesian statistics will be used even more so in the future?
Yes, I think the trend is towards using it more, and in many different areas. Not just in what you consider a strictly business context, but also lawyers, for example, will be having to face Bayesian statistics when they're trying to deal with cases in court.
Finally, addressing the college undergraduate student majoring in business administration, can you please share with them your opinions on the importance of understanding Bayesian statistics?
I think it is very important. As a point of view, it's not that complicated. It's not a difficult thing to understand. And so if you make the effort to learn it right away, you can begin to apply it right away. So it puts you in a position of being able to make decisions in the face of uncertainty, even such decisions as how valuable it would be for you to know this information. So maybe the student could even begin to decide after the fact whether he should be studying in a particular area, using Bayesian analysis to decide what are the costs or benefits for studying and for not studying.
Before we introduce Bayesian analysis, we're going to review some key concepts in probability that will help you understand how Bayesian analysis works. You should already have had a strong background in these concepts from prior courses in statistics. But this is a quick review to make sure you're on the same track. If you're confident that you know these concepts, you may want to fast forward and to move ahead to part 2, where we present Bayes' theorem. Part 3 of this program will take you through a real-world marketing problem. An outcome is defined as something that happens, an occurrence. The term universe represents all possible outcomes that may occur. Let's say, for example, that you're about to roll or toss a die. Getting an ace is one possible outcome. The numbers 1 through 6 represent all possible outcomes that can occur when you toss the die, and that is your universe. The term event is defined as a collection of outcomes. We might define an event as all tosses of the die that have outcomes less than 3. The random variable in this example is the number of black dots that will appear on the face of the die. We can find the probability of getting an ace by figuring out the relative frequency that this outcome should occur over the long run in a series of outcomes or tosses of the die. Let x be the random variable, with the possibilities being 1, 2, 3, 4, 5, or 6. If x equals to 1, that is the outcome that we get an ace when we toss the die. The probability of getting x equal to 1 can be estimated as a long-term relative frequency of getting an ace. Namely, if we were to toss the die many hundreds of times and we tabulate how many aces we got, and you divide that by the total number of tosses, the result will be the probability of getting a 1, which is 1 over 6, or 0.167. This means on the average, 16.7% of the time, you can expect an ace. When you're tossing a die, the probability of getting an ace remains the same for each toss, regardless of the outcome of the previous toss. Clearly, we find that the fact that you got an ace on one toss does not have any effect on the likelihood of getting an ace on the next toss. The events, or in this case, the number of dots that appear in the face of the die after each toss, are independent to each other. Joint probability tells us the chances of two events occurring simultaneously.
I'm recruiting freshmen for the marketing club. I try to recruit them as they enter the dining room. Some are male, some are female. Some are business students, while others are not. I want to know what the chances are of choosing a student who's both a business student and a male.
This question involves joint probability. Let x be the random variable representing the student's major, with the possible outcomes being business or non-business, or simply B and NB. Let y be the random variable representing student's gender, with the possible outcomes male or female, or M or F. If event 1 is defined when a student who is a business major was selected, and event 2 is defined as a male student being selected, we may want to know the probability of x equals b and y equals m. For convenience, this is written simply as a joint probability of b, comma, m. You can find the joint probability of two events by multiplying the probability of each event if and only if the two events are independent to each other. Once you have joint probabilities, you can compute marginal probabilities. Assume that the university admissions officer has given you a table of male and female incoming freshmen, both those who are planning to major in business and those who are planning to major in disciplines other than business. We can convert this table into a joint probability table by dividing each cell by the total number of students that we have, which in this case is 250. We now have a joint probability table. For example, it shows that the probability of a student being both female and non-business is 20%. Assume that we want to know the probability of all students majoring in business regardless of their gender. This is known as the marginal probability of B. To find this, simply add the probabilities for both sexes in the business column, which is 0.40 plus 0.20, which equals to 0.60. Mathematically, the marginal probability of B equals the joint probability of M and B plus the joint probability of F and B. If we add rows and columns, the margin totals are indeed the marginal probabilities. Conditional probability is usually written as the probability of X given Y. The item to the left of the vertical line is the probability variable, in this case X. The item to the right of the vertical line is the given, or the item being conditioned on, which in this case is Y. For example, assume that the recruiter for the marketing club, he wants to get more male business students. The conditional probability of selecting a business student from the male population is simply written as probability of X equals B given Y equals M. For convenience, we simply state probability B given M. This is called conditional probability, probability of business major given gender equals male. Mathematically, we can compute the conditional probability of B given M as the ratio of the joint probability of B and M divided by the marginal probability of M. Remember, the marginal probability of M is the event that we are conditioning on. We are assuming that M is given. Similarly, if you multiply your conditional probability of B given M by the marginal probability of M, you will get the joint probability of B and M. Understanding the relationship between joint probability and conditional probability is crucial to understanding how Bayesian analysis works. Here's an example. Assume that we want to know the probability of students majoring in business given they are male. What we are looking for then is the probability of B given M. Recall, we have joint probabilities for gender and major given by the registrar's office. The problem we face is, how can we convert from the joint probability table of B and M to the conditional probability of B given M? We do this by computing the marginal probabilities for male and then dividing the joint probabilities by the marginal. The probability of getting a business major is now clearly 2/3. We have converted from a joint probability to a conditional probability. We can then do this for all genders. Now that's a lot of information to digest. You may want to take some time and review this material, what we just covered. And you can come back and we can show you how Bayesian analysis will convert conditional probabilities. And finally, in part 3, we will present a marketing example. Let's say that we have a conditional probability. Bayes' theorem mathematically will allow us to invert or switch the conditional probability using marginal probabilities. We know the probability of Y given X and also the probability of Y. We want to find out the probability of x given y. Mathematically, the formula for Bayes' theorem looks like this. Probability of x given y is equal to the probability of y given x multiplied by the marginal probability of x and divided by the marginal probability of y. Note that we are switching the conditional probabilities. Let me give you a little background on Thomas Bayes, who he was. He lived in the 18th century, 1702 to 1761. I'm quoting from the Dictionary of Economics. It is often straightforward to pass from the probability of the particular given the general. Bayesian analysis allows one to compute the difficult probability of the general given the particular. As such, it provides a solution to the central problem of induction or inference, enabling us to pass from a particular experience to a general statement. This Bayesian inference applies generally in science, economics, and law. In fact, it's very interesting that Thomas Bayes was not a statistician. In fact, he was a Presbyterian minister. He only wrote one manuscript, and this was discovered 2 years after his death by a friend. When he found a mathematical manuscript, he submitted it to the Royal Statistical Society, and nobody took much notice of it. And now, almost 200 years later, let me quote what the Dictionary of Economics concludes about Bayes' theorem. It is hard to think of a single paper that contains such important original ideas as does Bayes. His theorem must stand with Einstein's E equal to mc squared as one of the great, simple truths. In fact, Thomas Bayes wanted to prove the existence of God based on, which is a general statement, based on the particulars, on the tremendous systematic ordering we have in science, such as astronomy and biology, chemistry, physics, and so forth. So the probability that this tremendous order in the universe would occur by accident is so low that you have a positive probability that supports the existence of God. So Thomas Bayes was a theologian. And yet we in marketing today find tremendous uses of his theorem. Let's look at an example. Assume that you decide to recruit students from the business school for your marketing club. You want to be sure to get females as well as males. So you'd want to know the probability of females given business. Now we're assuming that you're going to go to the business school and go to their cafeteria. You want to recruit females. The chances of selecting a female from the business majors can be computed with Bayesian analysis. In this case, we again will use information from the previous conditional probability problem. We know that the probability of business students given females, or B given F, is equals to 1/2. Assuming we are selecting from business majors, we are in the business school now, what are the chances of selecting a female student from this group? We can get the answer in 4 steps. Step number 1, begin with the marginal probabilities we derived earlier in the program. Probability of M is 0.6, probability of F is 0.4. Step number 2, multiply your marginal probabilities by the conditional probabilities. This gives us a joint probability table. Step 3, add the columns of the joint probability table so we can get the marginal probability of business and the marginal probability of non-business students. These are our new marginal probabilities. Step 4, divide the joint probabilities in the table by the marginal probabilities in each column. The probability of female given business major is now 1/3. Given business majors, we are less likely to find a female student than a male student. Bayesian analysis can be applied in a way that is very useful to marketing problems. Now, two important terms used in the Bayesian revision of probability values are prior probabilities and posterior probabilities. Prior probabilities is simply the marginal probability associated with a given event. Posterior probability occurs when additional information has been used to update or revise the probability, simply known as probability of the event given an observation or given additional information. In order to simplify this procedure, let's demonstrate pictorially what we are doing. What we do is to take the conditional probability, which is up, and our prior probability. From these we get a joint probability. Then we will derive a new marginal probability and use it with a joint probability, i.e. we divide the joint by the new marginal, to get a new conditional probability. And this is called our posterior probability, probability of the event given additional information. We'll come back to that diagram later. Now let's look at a real-world marketing problem.
In terms of the topic today of Bayesian statistics, we're looking for, in a way, I would think the student is, how can one apply that? Again, going over theory, one doesn't always get the full flavor and appreciate that. Since the emphasis is upon decision making, one of the starting points in statistics is if you had data and you had to make choices for a decision based upon different alternatives, and you have this information, you could really come to a number of different decisions if you did not have probability. Basically, there are different criteria. How the person feels. Are they pessimistic, optimistic? There are such criteria as minimax, maximax, regret matrix, and all of those are basically done without any statistics. Depending upon how the person feels, they would come up with different conclusions. What if we have additional information? And that additional information is in terms of probability. Remember that in terms of decision making, the more information we have about our choices, hopefully the better our decision-making process will be. But if we are limited in the amount of information, we have to do with what we have. So if we just have a certain amount of probability, that's better than not having none at all. And if we can go one step further and get additional information and revise those original probabilities that we were given, we can improve upon that. And Bayesian statistics is what that truly is. Using given information, using additional information, revising that, always trying to get more information and better information before we finally make a final decision.
Assume that your firm is considering whether to advertise a product or not. Of course, the key problem really is, does it pay to advertise? Will it increase your sales? If yes, by how much? And will the incremental sales be sufficiently large to make the advertising pay off? These questions will depend, of course, on the U.S. economy. This is known as an exogenous variable. Your two random variables are net sales, or sales minus costs, and we define that as S, The condition of the U.S. economy is our second variable, and we define that as E. Let us assume that your possible events for the condition of the economy are defined as economic growth, or E sub G, economic stagnation, E sub S, and recession, or E sub R. Then we clearly have a decision variable. Do we want to advertise or not? If we decide to advertise, we define the random variable of net sales as S sub A, sales when you advertise. If we decide not to advertise, then our random variable is S sub N, or sales, no advertising. Assume your payoff table looks like this. If you advertise and economic growth occurs, you'll earn $200,000. If economic stagnation occurs, you'll earn $50,000. If economic recession occurs, you will lose $100,000. Thus, if you decide not to advertise, your losses will be less and your earnings will be less too. Economic growth will enable you to earn $50,000 as your max. Economic stagnation will allow you to earn a max of $20,000, and if recession occurs, you break